Hey, welcome back. We'll talk about Merkle trees right now. So basically, still have the same goal as we had for Merkle-Darmstadt. We have a hash function for fixed length input, namely 2L, and we want a hash function for arbitrary length input. And we already did this with like this chain idea for Merkle-Darmstadt. And essentially, if you just want this hash function, this is sufficient. This works really well. However, there are also Merkle trees, like these, and they have some advantages that we will talk about now. So basically this thing works as follows. I have my input arranged in these blocks here. And again, similar to Merkle-Darmstadt, I had to pad my input so that I'm actually able to arrange them into these blocks. And what you need to notice is that these blocks form the leaves of a binary tree. So the numbers of these blocks need to be something of the form 2 to the n. So in particular, in contrast to Merkle-Darmstadt, we now have to pad, at the worst case, we have to pad just doubling the input length. But all of this kind of works, okay? This is fine. And now this Merkle tree works as follows. It always takes two leaves and hashes them. So every inner node of this tree will have a value associated with it, and that value will be the hash of its two children. So this node here has the hash of x1, x2. And then this goes on until we are at the root node. So then, for example, for this inner node here, by the same rule that it has the value of the hash of its two children, etc. So in the end, the root node also just hashes the values of its two children. And then the overall hash of all of these values is just the value of the root node. So let's talk about collision resistance. Ideally, if someone finds a collision in this hash tree, then we should also be able to find a collision for the underlying hash function h bar. So let's look at how this works. So let's say someone has found a hash collision. We can already assume that these two x's have the same length, because in the lecture, basically, we just did the trick that we did for the naive Merkle-Darmstadt 2. We just said that the hash value is actually not just the hash value of the root node, but we also just appended the length of the message. So if we have a collision, then for these two inputs, this value must be the same. So in particular, the length of the input must be the same. And all inputs with a different length have a different this, and so this would not be a collision. So disregard all of that. We just, through this argument, we already know that we will have a collision with two x's of the same length, in particular with the same number of blocks. So what we know, because this is a hash collision, we know that the hash value of both of these is the same. And now the question is just, where do we find our hash collision here? And essentially, we do it kind of similarly to Merkle-Darmstadt. We go through this whole thing, but now because it's a tree, we go through it layer by layer. At least that's the way that I think about it. That seems to be the easiest. So we start with the root node, and there we know that their two hash values are the same. And now we just look at the input to this root node. And we have two cases. Either one of these is not the same as the other, in which case we will have found our collision, right? Because now this hash function has this output, which is the same for both the black values and the red values. And otherwise, we go back one layer again. So if on this layer all of the values are also equal, then we go up one layer and we take a look at these values. So obviously all of the red yij primes that I put onto this tree, they are the values that we get if we compute them from the red x primes. And now on this layer, it may also happen that one of these pairs is different. And then in that case, we would have found our collision again, because by assumption, because we did have to go one layer up, we immediately get that the hash output of these hash functions is the same in both the black and the red tree. But if one of the inputs is different, then we have our hash collision again. And then we can do this again and again and again. We go one level up until we find this one layer where there's one yij that's not equal to yij prime. And in the first layer where we find something like this, we will have found our hash collision. And then similarly to before, you need to somehow argue that this will happen at some point. And here it's easy to see, because here it will at the latest happen at the leaf nodes, because there certainly one of these xi prime must not be the same as xi, because otherwise there's no hash collision for the overall hash 2. It just, you put in the same x twice and got the same hash value, which is, yeah. So to summarize, you look for the first layer where something is different in this layer, but in the layer before that, everything was still the same. And then you get the hash collision. And this needs to exist because at the latest, the leaf nodes are not all the same. Now, the fun thing about Merkle trees is the following. Let's say I have a huge data set. And let's say one of these data points is x6, and that's the one that I'm now interested to showing you is part of this data set. So basically, you're sitting around, you have the hash value of the Merkle tree, so essentially a hash of this huge data set. And now I'm coming to you and saying, okay, hey, by the way, x6 is part of this data set. And what I could clearly do to convince you of this is I could just give you all of the x's, so all of these blocks, and you would just be able to recompute the hash and see, aha, actually this is true. This whole data set conforms to this hash that I have, and x6 is part of it. So now you're convinced that x6 is actually part of this data set of which you have the hash. But kind of the nice thing is that I don't actually have to give you all of the data, so the whole data set, but you can check this much more efficiently whether x6 is part of this data set. And for this I claim I can just give you x6 and x5. I also give you this hash value and this hash value, and then that's it. This root hash value is something that you already have. And I'm giving you the green values. So these are way fewer than all of the 2 to the n blocks. I'm just giving you, for every level, I give you one hash value. And well, for the leaf node, I also give you the sibling dataset. And now what you would do is you would take these two values and hash them. So now you have this hash value here. Now you take this green hash value that I gave to you together with this hash value that you have computed, and you hash it again, so that now you have computed this hash value. Now again, you take this hash value that I gave to you, together with this hash value that you have computed, and you will recompute this value, and you will just check whether this is equal to the y01, so to the root hash that you already had. And if this is the case, if I was able to provide you with all of the green stuff so that recomputing this part of the tree actually gave you the same root hash as you had for the complete data set, then everything will be fine. Then you should be convinced that x6 is actually part of the complete data set. Why is this? Let's say I took some x6 prime, some other block of data that is not the same as x6, and I wanted to sell you this as this is part of your dataset. Then I would have to come up with all of the green values. So I'd have to give you some x5 prime plus some hash value for this and some hash value for this, so that overall, after you recompute all of this stuff, you will get the same root hash. So let's say I succeed in this. I give you all of these values. And at the end, you're convinced that actually the y01 prime that you compute out of this is the same as the root hash that you had, the y01. Then we can go up one level and look at the hash values here. So this value that I gave to you and to this value that you have computed from the other values I gave to you. And if they are not the same, then you will have found a hash collision. And if they are the same, we go up one level again. Then we take a look at this level before that, at these two, and again compare this. Then it may happen that the black values from the original tree at the point where we had all of the data and hashed this, right? So someone at some point created this complete hash, and that person also knew the complete data set, in particular the x7 and x8. And there was like the original Y24 value that came out of this. So of the original hash of the original dataset. And now if I give you a different hash for this, then we will have found a hash collision for this level. And then again, with the same argument, this whole process ends at the latest at these leaf nodes, because in the original dataset, there was x5 and x6. And in this new fake dataset that I came up with, if this still happens to be the same hash value, then at the latest we have the hash collision here between x5, x6 and x5 prime, x6 prime. So overall, if I give you some cleverly chosen data points from this tree, you can easily verify that this one block that I gave to you is part of the whole dataset without having actually to hash the whole dataset. And an interesting example for this are actually blockchains. Interestingly enough, they are not just chains of hashes in blockchains, they are also these trees of hashes. So if we take a closer look at Bitcoin, for example, there the structure is essentially the following. So blockchain actually follows this idea of Merkle-Darmstadt mostly. That's what we have right here. So we always take the hash of the previous block and make it part of the hashed value for the next block. So we have this chain of hashing there, which makes sense because it's a blockchain. However, the other part of this input, so usually we would have, in Merkle-Darmstadt, this would have been like the xi, so the ith block of the input. This is not actually like the set of all transactions that belongs to this block, but the set of all transactions that belongs to this block is just a hash value again. And this hash value is a Merkle tree hash of all of the transactions. So the transactions are the leaf nodes of this Merkle tree. And then there are a bunch of other values that are also part of the block, so that are also input to this hash function. And those consist of like a version field, then a timestamp of when this block was created, then the difficulty target, doesn't matter too much now, and a nonce, like a random value. And I guess the most interesting part would probably be the nonce. So the idea is that these block hashes have this special form. I think I've talked about this before. You would hope for that the hash value of your block would start with a bunch of zeros. Essentially, you get to mint the next block, so you get to add the next block to this blockchain if you find a nonce that will make the hash value look like this. And this difficulty target, it's called bits in this table here, that's basically saying how many zeros need to be at the beginning of your hash value. The larger this value is, the more difficult it will be to actually find a hash that starts with that many zeros. So you can imagine that like every second hash roughly starts with a 0, and every fourth hash starts with like a 0, 0, etc. So the probability of finding a hash that starts with like 16 zeros should be something like 2 to the minus 16, and then basically you try with different nonces again and again until you find these. Okay, but anyway, why are these transactions in this Merkle tree instead of just part of this hash? And the answer is exactly because of this cool capability of Merkle trees to make it easy to demonstrate that something is part of this dataset without having to check all of the other values in this dataset. The thing is, there are like a bunch of transactions in this. So if I basically buy something from you, I would want to be able to tell you that my transaction that is giving you money is actually part of this blockchain. And then for this, I actually do exactly this trick. I give you my transaction, and I also give you all of the other nodes of this Merkle tree that you need to be able to check that this is actually part of this dataset. So even if there are like 1,000 transactions in this one block, you don't actually hash all of the 1,000 transactions. You just need to hash log many of those to check that they are actually conform to this Merkle root of this one block in the blockchain. So that's already that. So the overall message is, if you use Merkle trees, you get these nice extra features, and they are like really convenient in a lot of contexts. If you don't need these extra features, you can probably just go with the Merkle-Darmstadt construction if you just need a hash of some data value. Okay, that's it for Merkle trees. Thanks, see you.